Coordinate geometry relies on precision. If you only have a relative proportion, you need a method to determine a precise location along a slanted line. Let's define the geometry. We place a line segment on a Cartesian plane, bounded by point A at coordinates x1, y1, and point B at x2, yq. Now introduce a third location, point P, with unknown coordinates x and y positioned on that line. Point P divides our line into two segments, AP and PB. The ratio of their lengths is given as m to n. Our objective is to calculate the exact x and y coordinates of point P using only the endpoints and that specific m to n ratio. Rather than memorizing an equation, we can derive the formula by applying geometric principles. The difficulty lies in the slant of the line. Because the x and y values change simultaneously, the variables are linked together. To solve for the point, we must decompose the problem by splitting the slanted path into two independent one-dimensional projections. We will isolate the axes by breaking the diagonal movement into vertical and horizontal components. From point P, we drop a dashed line parallel to the y-axis. Then we draw a horizontal line from point A. We mark the intersection as point Q, which forms a 90-degree angle. This forms right-angled triangle AQP. Repeating this for the upper section, a vertical line from B and a horizontal from P creates intersection R, completing triangle PRB. Through this alignment, we identify the corner coordinates. Point Q is xy1 and point R is x2y. The horizontal legs of these triangles now represent pure movement along the x-axis, separated from the y-axis. By constructing these triangles, we have successfully isolated the x and y dimensions. Next, we must establish the mathematical relationship between these two triangles. The horizontal baselines, AQ and PR, are parallel to the x-axis. The slanted line segment AB acts as a transversal cutting through them. In geometry, corresponding angles created by a transversal are equal. Therefore, angle A and angle P are identical. Both triangles also share a 90-degree right angle at Q and R. This satisfies the angle-angle similarity test. Because two angles match, the triangles are mathematically similar. Since they are similar, their sides scale proportionally, maintaining a constant ratio. Because of this similarity, the ratio of the two hypotenuses, AP over PB, is equal to the ratio of their horizontal bases, AQ over PR. We know the hypotenuse ratio is m over n, so we can substitute those variables into our equation. Let's define the horizontal base lengths. Subtracting the x-coordinates reveals AQ is x minus x1. By the same logic, the upper base, PR, is x2 minus x. Substituting these back into our equation gives us a formula using only the known ratio and x-coordinates. We perform the same subtraction process for the vertical heights, PQ and BR, using the y-coordinates. This results in a parallel equation for the y-axis. M over n equals y minus y1 over y2 minus y. The geometric shapes have now been translated into two solvable algebraic equations. To isolate x, we cross-multiply and rearrange the terms. Simplifying provides the final expression. X equals m times x2 plus n times x1 divided by m plus n. Repeating this for the y-coordinate yields the corresponding formula for y. This pair of equations is the section formula. The symmetrical x and y formulas demonstrate how coordinates scale identically. Using our earlier example of points A at 2, 2 and B at 8, 8, you substitute these values directly into the variables to find the exact location of point P. This math is bidirectional. If the coordinates of point P are known, you can reverse the process to find the dividing ratio, m to n. The section formula is a mathematical consequence of triangle similarity, providing an algebraic method to navigate proportional geometry.